we can begin, I guess.
Thank you. So today, I would say it's maybe the most technical part of this lecture series. So we're going to see how to go from Airy structures, and particularly the one we constructed last time, to the spectral curve description. And for all these constructions that come from VOA, there's a procedure which is pretty automatic. You just have to compute. Sometimes it takes 10 pages or a bit more. But the idea is simple. So I recall that we were considering some Airy structure coming from twisting the Heisenberg algebra by the full cycle of order R. And we were describing our W generators in terms of these fields, VAX, which was diagonal for the automorphism. So it means that here you have fractional powers and the automorphism is acting by roots of unity. And here I have GRK over XK plus 1. A is running from 0 to R minus 1. And JK, so it was a representation of the Heisenberg algebra in terms of differential operators. So H bar 0 dxk for k positive. For our purpose, the zero mode was 0. And here we just take x minus k for k negative. And out of this, we had seen that for I, which is in 1R, we computed or I gave the answer for the W field. So I will rewrite it here. So I factorial, there was a sum over pairs, so I have some combinatorial factor. So all of that was coming from the elementary symmetric in the fields attached to the orthonormal basis of the standard basis of the Cartan. And this VA was a Fourier basis that allows us to diagonalize the action of sigma. So for that reason, we had some of the roots of unity that were coming from going from this VA basis to the standard basis in which the W fields were elementary symmetric. So here I have my sums over roots of unity, psi ij, a 2j plus 1 ai. Then I was having these quantum corrections coming from ordering, from normal ordering, and the product of the V fields at X, normal ordered. And the Airy structure equation was telling us that Wi X, so I can expand it in modes, or xk plus I. So here there were only integer powers. So the Airy structure equations are saying that this is 0. That determines the partition function for all I and k, which in that case were such that there is some lower bound depending on I. And in the Airy structure I constructed, in fact, we had that k was bigger than R I plus, let me see, KR plus I minus 1 S. when I needed R to be congruent to plus or minus 1 modulo R.
Which is the elementary symmetric function here?
So Wi of x was elementary symmetric of what I denoted chi1, chi R. And this chi is obtained by Fourier transform to get to the VAs. So I'm just repeating what we had last time. And we're seeing we were successful in constructing Airy structures only when we were selecting exactly those modes. But what I'm going to say for the moment is you can just ignore Airy structures, all these conditions. Just imagine that you have this collection of equations and we want to translate it into some identities, some constraints for correlation differentials living on a spectral curve. So I can rewrite that by saying that Wix acting on exponential of f. So you see, you have to have k which is big enough to have a constraint. That means that this is going to be a small o of x to the minus di. And since I had these fractional powers that I don't like too much, I'm going very quickly to shift to the z variable. So x is z to the r. Intermediate. Yes. Is there a question? Okay. So it means that this is a big O of z to the minus r di. Okay. So good. So now we are saying that something here in the variable z or x can be meromorphic. So there's no, there cannot be very negative powers of z. It just stops somewhere. So it means that some object is meromorphic on the curve, which is C, which is simply spec of CZ. And that has a projection to spec of CX. So that's the base. And that's the spectral curve. So we learned that this quantity is meromorphic with poles of control order. So to translate that into differential, it's really just a translation. There's nothing really deep going on here. It's just a rewriting. So we're going to introduce, so we have this f, which is a sum of all genus and n. So this is a formal function. I can write its Taylor coefficients.
Yes. I just want to understand this notation, spec of C of X and spec of C of Z. What is the base curve? What do you mean by spec of C of double?
So you can think of it, if you don't like the spec, just think this is a small neighborhood of 0 in the complex plane. I forget.
It's not really a curve, it's just a local curve.
It's a scheme. But if you don't like that, you just say it's a small disk near 0.
So the significance of the diagram is just to indicate the branching?
And this X is a degree R map. Locally, it looks like Z to the R. So the Z plane, 0, and here I have my little disk. And here I map it. So if I have a branch here, it's going to be like this. All these maps to the same positive real axis here, intersected with small neighborhood of 0.
I guess I'm always a little uncomfortable with this local global business. So when you say that it's meromorphic with poles at
That's zero.
particular order, are you only speaking about those poles which are somehow in a neighborhood of zero, or
Yes.
I don't see the global local transition.
So far, I'm explaining how to attach a spectral curve, which is going to be a local spectral curve, to an Airy structure. And what we actually see is that if you take any global spectral curve with a branch cover map X to base, say, P1 or C or some domain of C, you can zoom in, you can just take little neighborhoods of the ramification points of X. And just all the objects that you have, meromorphic forms and so on, you just remember their local expansion near those points. And if I do that, I can attach to a global curve a local curve. Does that answer your question?
You just said P1, that I understand, but that's not the same as spec of CX.
Yeah, but if you have, so you have your Riemann sphere here, and here you have your global curve with some map, so of some degree. Then you can look at the zeros of the X, collection of points, AJ, and so it is zeros of order, let's say Ri minus 1, let me call them like this. Then what I'm saying that take Ui, which is a small neighborhood of alpha I, and then locally your picture, so you have a local curve, which is a union of these Ui, and you can restrict X to be in the union, of the XUI. And all what we do in topological recursion, for the residue formula, it's enough to work on this C local. What allows you, so you first compute some meromorphic forms on the C local, so they're only defined in these little open neighborhoods. And then you will see in a moment that the thing that allows you to define them globally on the curve is using the Bergman kernel, so omega 02.
So there does exist some globally defined curve.
So for me, when I have an arbitrary Airy structure, there's no question of whether this series expansion converge or not. So it's enough to work either with spec, or if you assume that series have non-zero radius for convergence, it's in little neighborhoods like this. And it could or not come from a global curve. But the converse is always true. If you have a global curve, then there exists a local curve to which you can apply what I'm going to say.
But when you express these these differentials eventually for the topological recursion, or the correlation functions or whatever, in terms of either Z or X coordinates, are these Zs globally defined, or are they just a different Z in every neighborhood?
So initially not, but if you have an omega 02 which is global, yes, it does. Maybe I can come back to that in 10 minutes when I write down what the role is played by omega 02 here. Okay.
Okay.
So we have these expansion coefficients, and out of that, if I take any f of this kind, I can encode it in omega gns, which is, so now it's for fixed Gn, it's going to be a differential form in n variable. And what you do that you just take these coefficients fgn, k1, kn, and you replace formally xk by d psi minus k, where this is a certain basis of neuromorphic one forms I'm going to specify. So this object depends on n points on the curve. And if the d psi minus k are linearly independent, you don't lose any information in doing that. Okay, so now, even if I don't specify yet what are those d minus psi k, you could say, since I didn't lose any information, let us see what are those constraints meaning in terms of the omega GNs. So at the end, everything is expressed in terms of these Heisenberg operators, the JKs. So let's make a generating series for them. So JK over Z, K plus 1. And I want to make it a differential form, dz. So this I can write J plus J minus, where this contains the negative, so the negative powers. Oh, sorry, this one is the positive powers. Of Z, that means the negative modes. And this one is the opposite. And in the construction of Airy structure, the last step that we did was shifting those modes, the dilaton shift. Otherwise, if we were just working with the usual JKs, we would have just obtained some differential operators of homogeneous degree I. And we didn't want that because we wanted a degree 1 term of a very specific form plus something else. And to break homogeneity, we had shifted the JKs. So when we do this shift, so RWI.
Sorry, but so the sum is not over only k greater than 0?
Yes, it's over all integers. Thank you.
Okay.
So what we actually did was conjugating these ones by some, so let's call that HIX, where U was, so shift of variable that's amount to some, so it's JK is the, for K positive is the differential operator. So when I exponentiate it, it corresponds to shifts. And there are some coefficients I'm going to call F01 minus K. And then there was this freedom of conjugating by a purely quadratic differential operator. So I call these coefficients F02 minus K minus L. There's an H bar and then GK GL over 2. So
this is, I know you didn't speak at all about fermions, but to help me understand, is this object omega interpretable as a vacuum expectation value of a product of the J minuses evaluated at the various points?
No, I think what you have in mind is the vertex operators, so these fermionic operators, and I'm not using that. Well,
in the only case
okay,
that I'm
yes.
familiar with
Yeah,
It
okay.
is-
If you
the
want,
omega is expressible as a finite product of the j's evaluated at these various.
okay, if you take this
z-axes.
one to be 1 over zeta k, then you start to, and you forget about this second part. Then you recognize at least the positive part of some fermions.
Well, the positive.
Yeah, just one part.
Okay.
So we want to know what's the effect of this U on the J. So as I say, this is shifting. So this one is shifting the negative JK because the negative correspond to the XK. So we shift them by a constant, which is this one. And this one correspond to replace some negative mode by negative mode plus something positive. So this J of Z becomes J plus J minus plus something I would denote omega 0,1 of Z, where omega 0,1 of Z is the sum over k's of the F01 minus k. And here we denote d psi k. D psi k is just a pedantic notation for z to the k minus 1 dz. So that comes from shifting the negative modes, therefore the positive powers of z.
All right.
Yes. Okay, just a parasite. So the J plus of Z, this I can rewrite. So here I do nothing. I just, instead of having Z to the K minus 1, so for the K negative, correspond to positive powers of Z, I just write it as D psi KZ. And the J minus of Z now, because of this, it's going to get shifted. And so here we obtain sum over K positive J minus K D psi minus K, where is D psi minus K is dz or zk plus 1 plus sum of f02 minus k minus L over k dxl of z. Okay. And this, if I want, I can rewrite as the residue when z prime goes to 0 of the primitive of some omega 02 times dz prime over z prime k plus 1. And omega 02, I define it to be the double pole if I just have this term, when I compute the residue, I get exactly, by Cauchy residue formula, I get exactly this term, plus the sum of the F02. Here I don't think I have KL.
So when it's a global and compact curve,
Yes,
is omega 02 Baker's quadratic bidifferential?
exactly. It's not, it's a bidifferential, not a quadratic.
Yeah, bidifferential.
But exactly, that's where I want, that's where I can answer your first question. If we had C is a global, so curve, and omega 02 is a fundamental bidifferential of the second kind. Which just means that it has a double pole on the diagonal. with coefficient 1. And therefore, it must have an expansion of this form when you expand around any point, in particular the zeros of the x.
So you said A, the
Yes.
definite, the indefinite article, but if you
Yes.
have a curve, and I mean a compact curve, then and if you normalize this thing, so that
Then it's an affine
whatever the A
space.
cycles are, that's unique, right?
If you normalize on some cycle, it becomes unique. Otherwise, you can always add a holomorphic bidifferential.
Right.
So it's an affine space of finite dimension.
Okay, thanks.
So if you had a global curve and some omega 02, which you may be more familiar with, then this one is the expansion to all orders when z goes to some zeros of the x. It defines for you some coefficients f02, and that's exactly the one I want to put in my Airy structure inside here.
But Gaetan, sorry, one question. But in principle, it can be just any coefficients, because
If I start just from my W constraint here, it can be anything. It just have to be symmetric.
yeah, so
Yes. And this is why I'm saying that local is more general than global. And local is a specialization of global. Global specializes to local, but not the converse. Okay, so this is a lot of notations. But the summary is that this J gets a term which is some omega 01 that encodes which of the dilaton shift that we get, that we decided to make, and which basis of differential we should use. This is the Dix case specified by this thing which we call change of polarization. So it's a change of omega 02. Okay. So now reformulation of W constraints. So we have this operator here, and we see that everything combines well when I want to express that in terms only of these J's. The only thing that may be puzzling is what are those roots of unity doing? These come from the geometry of the curve. You can encode them in the geometry of the curve. If you have a point Z, you can look at the fiber above x of z. And in this special local coordinate where x is z to the r, this is z, theta z, theta squared z, theta r minus 1 z, where theta is the rth root of unity. So this sum, which I get here, is going to be actually a sum over subsets of cardinality I of the fiber. This thing that we see here is going to look like, so maybe I should rewrite what was this psi I. Psi ij. So that was this thing coming from normal ordering. So up to some factor, it was a sum M1 Mi Maybe I should get it right. I want to write something correct. Where is it? Okay, so my psi was that 1 over I factorial sum over this, and then the product of theta m to L minus 1, theta m to L over theta m to L minus theta m to L minus 1. And then the product of the theta minus ML AL. So we see we have this inverse square of difference of roots of unity. And here we have also 1 over x squared. If I was making everything a differential form, so multiplying by dx to the I will have factors like that. And so up to a factor of r is going to be some d0 z squared. So what I recognize here is omega 02.
Sorry, Gaetan, in the previous psi ji, there were all of these integers a that you're summing over, and here you have thetas. So what is the relation?
Yes, they are here. The a's are here.
Oh, the a's are the n's?
No, the n's I sum over, and the a's are here.
Ah, okay.
So if that term here, I call it omega 02 standard, it was the one that we got before doing the change of polarization. We're going to see this type of things coming from theta m2lz, theta m2l minus 1z. So now I can come to the form that at the end it takes. Okay, so this HIX is, instead of a sum over A's, I'm going to get a sum over all ways to look at cardinality I subsets of this fiber. I still have my sum over pairs. I will have some h bar to the j, 2j, j I minus 2j. Then I have the product from 1 to j of omega 02 z 2l minus 1 z 2l. So that's the elements of this set.
Is there an I factorial in the numerator?
There is no I factorial because it disappeared also with what I had in the W. Then, so in this V, so the V we can express in terms of these J's, and this J will also have these omega 01 terms. So we can try to write it separately. So I'm going to have the sum over partitions of the remaining A indices. So that's 2j plus 1 I. And here I have the elements which take omega 01, the elements that take, so I can maybe write, that takes j plus zl, and the elements that take j minus ZL. And that you can write again in a different form, because after all, this is a sum over pairs. So you can also say this is sum over cardinality I subsets of the fiber. And then the composition, so sum over all pairs. And then you want that the union of all these pairs, union with A0, union with A plus, union with A minus. So doing it in this way, so this should be Z, the set that we have here. And that has the effect, rewriting like that, of removing all the factors, combinatorial factors. So omega 02 for these pairs, omega 01 for elements in A plus, so in A0. J plus, J minus. So that's our operator, and we want it to act on exponential of f. So when acting on exponential of f, so this contains many x's. So these x's are negative j's. And we act by some, so these guys contain the positive mode, so the differential. And this is a combination of x's. So we act by differential operators. We pull down from the exponential some fgn's. They will come with a certain number of x variables. And at the end, we want to identify the coefficient of some monomial, the one with exactly n of these x variables. And then we want to convert it, to convert each xk to dxi minus k of some variable. So that's on the terms involving n monomials of this thing. And this gives some rather complicated thing. You have to collect all the pairs of h bar and so on. But let's just do r equal 2 so that you get a feel of what it is. If you collect that and collect the coefficient of h bar to the g, you're going to find that omega g minus 1 n plus 2 z z z1 zn. So these come from the replacements of the variable xk's here for each of these on these monomials, plus the sum of genera and the way to partition this z1 zn into two pieces. And here we'll have omega h1 plus j j omega h prime 1 plus j prime. So z and z prime, maybe z prime and z prime prime. And maybe to be consistent, I put the double primes here as well. And here we must have a sum, so r equal 2, and I'm considering the case r equal 2, because the r equal 1 is simple. It's some over a subset of the fiber of cardinality 2. So you have to take some z prime, which is in f of z. So that's the result of action of HR, and you want that this is a big O of z to the minus r, which is 2 delta 2. Whatever this delta was in your initial constraints. For higher r, well, you just see more terms. You see omega, 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 omega plus, etc. And you're going to sum over these cardinality I subsets. Yeah. And this is what we call the abstract loop equations. The fact that these particular combination for any I, you control the order of the pole. And that's what you want to solve at the end. And so now the theorem. So all what I describe here, this is done in detail in the paper with Vincent Bouchard, Nitin Chidambaram, Dima Noshenko, and Thomas Kreuzig, which I already mentioned last time. So if these equations have a solution, it must be given by the topological recursion, so the spectral curve. Topological recursion. So for R equal to, this is the Chekhov in our Rantin form of the recursion, which is omega gn plus 1 z1. Maybe I write like this. z1 zn to be closer to what we had is the residue at z prime equals 0 of the integral of omega 0 2 up to z prime. Here you divide by omega 0 1 of z minus omega 0 1 of minus z. So y minus z, it's exactly the other point in the fiber of f of z, the fiber of z in that case. And here you would see g minus 1 n plus 2, z minus z, z1 zn. And exactly this sum, so I'm not going to write it, except that you don't want omega 0 1s. So here I could also have omega 0 1s. In that case, this contained something omega 0 1, omega gn plus 1. And you precisely want to use that to isolate omega gn plus 1 and compute it in terms of the omegas that you know from induction. And so this is a recursion. And for higher R, this is the Bouchard NR recursion. There's also a similar recursion kernel. Now there's a sum over I as well. But the idea is the same. So to give an idea of how you prove that, so assuming the abstract loop equations, how do you solve them? Well, what you do is that you use some combinatorial identity, which essentially comes from the fact that when you do u plus this hi of x, or maybe with a, say, minus u, sorry, I want that, sum of the hi u to the r minus I. So you do degenerating series. And remember, these ones were coming from some conjugation of something that were elementary symmetric. Essentially elementary symmetric in the J's. So this thing here if you specialize to u, which is minus omega 0, 1, this minus omega 0, 1, you can always define the S, which is the minimum of, what is the first dilaton shift that you did? And then this guy is going to behave like a constant z to the s. That's by how you defined omega 0, 1 in terms of these f01s. Okay, so you also know when you do this specialization, on the other hand, this guy is a big O of something. And this omega 0, 1 z to the r minus I is a big O of z to the r minus is. It actually combines to give you that this combination here is of a certain modified order. Actually, in that case, I think it's the same. So that's the first idea. But then, because when you do this, so since that thing was elementary symmetric on some j, it's a product of u plus j. So if I set u to some variable, it's like shifting j by something. So this is also equal to some omega g n plus 1, and here the product over all differences of this type for the all elements in the fiber except z, plus something involving only omega j prime and prime, which are smaller. And you know that this is controlled. And the final step is to say, okay, now I write, there's one thing I know about these omega j and the way I define them. It's expressed on the basis of dxi minus k. And the dxi minus k, we were knowing that it was obtained by integrating omega 0, 2. So this formula here. So I can write a Cauchy residue formula to say that this omega j in respect to the first variable, it must be the residue when z goes to 0 of the primitive of omega 0, 2. So it's up to z prime, when z prime goes to 0, of omega g n plus 1. So it's a Cauchy residue formula, which holds by the way you defined the dxi minus k. And now you isolate omega gn. So you divide by this, you put everything on the other side, and the big O that you don't really know doesn't contribute to the residue. Because the pole which may exist here is compensated by the possible zeros that you have from these differences.
So I'm a bit confused. You have gn plus 1 on the left.
Yes.
And you also have gn plus 1 on the right. So where is the recursion?
So far I just wrote the Cauchy residue formula. But now here, I replace that one by the expression I get here.
Ah.
And the role of that is to say that, when you see, to know what this formula means, that to know omega gn plus 1, you just need to know its behavior at the poles. So it's a local computation. And for that local computation, you can use that information that tell you that omega gn is something that you already know, plus something that you only know it has a pole of a certain order. And that order is going to make that this term doesn't contribute to that formula. And that way you get the recursion.
But in the end, it's just a finite quadratic polynomial recursion, right?
Yes. So this was unknown and it disappeared. Oops. Okay. So this is the process by which you convert W constraints to usual spectral curve topological recursion. Are there any questions on this?
Well, could you just for this is a sort of a museum, could you just say, amongst the examples that we've seen or that we know, which fit into the R equals 2 case and which require R greater than 2?
So that I guess you will see next talk, where I'll give applications. But before 2013, all applications of topological recursion were just needing the R equal 2 case.
So the random matrix examples were all R equals 2.
Yes.
The symplectic volumes example was also
Yeah.
R equals 2.
Exactly.
And
You just need simple ramification, and you could say it's generic. If you take a generic cover, it will have simple, dx will have simple 0, so that should be enough. Now, the first example where you need this higher version, and maybe the only one, is the Witten R-spin intersection numbers. In that case, it's exactly y equals e to the r. Sorry, x equals e to the r. And you need y equal, omega 0, 1, which is z to the r plus 1 dz.
so there's something also called R-spin Hurwitz numbers. You don't need R greater than 2 for that.
No, surprisingly, you don't.
And
Because
also,
what's happening is that when you have when you have this cover, in the R-spin case, so you have, I don't know if it's R or R minus 1 branch points, but they're all simple. They don't collide.
and also for the orbifold examples.
Also for the orbifold.
Yes, the same. In the 5 remaining minutes, I want to say a word, so that was a question of Nikita last time, about what happens for other automorphisms. So here there was some work of Vincent with one of his students, and a parallel work that we did with Rainier and Yannick Schuller, who was a master's student, who is now a PhD student with Andrea Brini in Sheffield. So this is from last year. It's essentially a lockdown paper. So imagine you apply the same procedure when now you take your sigma, which is a product of cycles. RD minus 1 plus 1 RD. Now you can have a Fourier basis for each of this cycle. So you're going to have a collection of variables x, mu, k, where mu is from 1 to d, corresponding to each of these cycles, and k is positive. So you have d copies of the Heisenberg. And you can compute what are the W generators, and you at the end have to do some dilaton shift. So you can try to do a dilaton shift. So it's enough to study just the minimal dilaton shift that you can do. So just shifting one. So let's assume that you shift this one by at the index S mu with some constant T mu. And then you ask yourself whether you can get Airy structures from that. And the answer is rather constrained. And somehow this is quite surprising. So here is what we know is true. We believe it's a complete classification, but we cannot prove it. So first, for each mu, you want this S mu to be between 1 and R mu plus 1. If you go bigger, it's much less interesting. Some of the partition function is trivial. And so let's assume that D is bigger than 2 because it's the case that we haven't treated, so at least 2 cycles. And then if you say, so you're going to order, you can always order the mu such that S mu 1 over R mu 1 is smaller than S mu D over R mu D. And then there's some congruence conditions. So the first R in this order must be congruent to -1 modulo S mu 1. Then all the intermediate ones S must be minimal, so equal to 1. And R mu D is congruent to 1 modulo S mu D. And moreover, T nu R mu should be different from T nu R nu whenever there's some resonance. Then we get an Airy structure. And there's some no-go. That means if you violate some of this condition, we can prove there's no Airy structure by saying that F03, for instance, is not symmetric, or F04 is not symmetric. And this corresponds, you can also do the spectral curve description. It corresponds to the spectral curve equation. So I will write like this. So initially, when we just had one cycle, we had, so if I write omega 01, which is y dx, that means that y was sz to the s minus r, so y could have poles. And so I had an equation which was x to the r minus s, y to the r was equal to 1. So that's for d equal 1. But in general, you have a singular curve minus so y over t mu minus s mu r mu minus 1. So you have that curve. And this theorem tells you actually there's a way to define TR for also for singular curve, but only for those ones. So only when the singularity, in fact, what you do that this is a curve C, you work on the normalization, which is a union of these curves. So this union of these ones. And in this theorem, which I wrote here, I said if the loop equations have a solution, then they must be given. It must be given by the. But there's no reason that the solution exists. What makes the solution exist is the fact that you have an Airy structure. So it's implied by having an Airy structure. So it could be that you want to solve such equation, and for example, when you take something that doesn't come from an Airy structure, so F02 is not symmetric, then it means that these equations don't have a solution which is a symmetric form in n variables. So here it is the same. We can define TR on those singular curves and not on others. And so it's for me, it's a mystery. So for the algebraic geometers in the room, what is special about the geometry of these singularities when R and S satisfy these conditions? Is there anything special when you do the resolution of singularities of that would somehow explain that? So you cannot construct an Airy structure. It also means that you cannot construct in a naive way a Frobenius algebra or a Frobenius manifold from deformation of these singularities. So it's a big mystery for me. What happens in the other cases? Maybe it's a definition of TR, but it's not naively working like this. So I cannot tell what this is. So I apologize. This was a bit technical today. It should be more smooth next time because we'll talk about applications of how TR connects to intersection theory. It will be more of a review of what is known.
So who is responsible?
I think me. So let's sync the speaker.
Okay, thank you, Gaetan.
Thank you, Gaetan. Thank you.
Thank you, Gaetan, very much.
I have a short question, actually also technical, I must confess. If we come back to this, let's call them canonical transformations,
Yes.
unitary operators. In principle, we can make it not only with quadratic, right?
Yes.
So in principle, we can add their, say, cubic terms and so on.
Yes.
And this will result in the operators of higher order.
Yes.
Also, of course, it will not be an ideal. It will be just a real algebra, because if we had Virasoro algebra, it stays Virasoro algebra.
It's conjugation, so you respect the algebraic structure.
Yes. But still, it somehow, I think, fits into the scheme that basically you have higher order operators, and these higher order operators nicely commute.
Yes.
Produce
So
some algebra.
what you can do is you can do this. So after all, you can conjugate by everything. So something I will call phi gn. And there's some indices, so A1, AN positive. Okay, maybe I call that L, then in that case, this is K1, Kn. So I can put some coefficients here. With some power of H bar. Maybe G. Okay, let's write Gn. Okay, and GK1, GKn. So that preserves Airy structures. And what it corresponds to, you still have the abstract loop equations, but now it's not true anymore than omega Gn is in the image. So that they don't respect the polarization. Plus some term. Phi tilde, it's related to phi, but not exactly phi. And therefore, what it means that you have these extra terms you solve.
But we might have an operators of all orders. So the operators, the first order will produce phi 0, 1, then next omega 0, 2, and so on.
Yes, so that will come up exactly in here. This phi will tilde will be expressed in terms of the phi's. And the way it is expressed is by this blob topological recursion, which express the general solutions. So something that I had written with Sergei Shadrin. The general solution of abstract loop equations. So we did it in a quadratic case, but if you have higher order, that's always the same. Is expressible by a formula which is not TR, it contains more terms. And that's what the blob TR does. And if you decide it to be normalized on omega 02, it corresponds to only allow these linear and quadratic operators, and you land back on TR.
Yeah, but I have an impression that somehow it's in some sense a bad choice.
What is a bad choice?
No, not a bad, but something that is actually some red herring. So it's not what we want when we are talking about W-algebras.
These higher order stuff?
Yes, if we conjugate with these higher order operators, but we conjugate just normal quadratic operators. So that's
Yeah, exactly. You're not going to reach W-algebras from that. You still remain in the world of Virasoro.
yes.
So just for certain application, essentially the most general unitary invariant matrix model, not the one with linear trace in the exponential. So if you have at least cubic, powers of 3 traces, then you need all these blobs. All of them. If you stay with something linear, linear trace plus quadratic trace, then usual TR is enough. So only the phi 01 and phi 02.
Okay, yeah, so sorry for overtime, well, but thank you for your talk. So thank you. I have to leave also, so everyone has to walk away, unfortunately.
Thank you.
Are there any questions to speaker? Okay, if not, I will stop recording and let's sing this